All right, so we are going to move on here to our second half of the unit and move away from talking about electrons to talking about gases. And we're going to start off by looking at some of the physical properties of gases with which we are already familiar. So, when we describe gases, we know gases are a state of matter that have a very low density. It's about 1/1000th of the density of a liquid or solid. That it is composed of particles like atoms and molecules, that these particles are in constant, rapid, random motion, and the amount of motion is dependent on the kinetic energy or the temperature of those particles. We know that gases fill up the space that are given to them, and they are capable of diffusing through the space that they are given, and so this leads to spontaneous mixing of gases. All right, so those are things that we actually already know, but there's a couple of properties that we want to take a very close look at as part of this part of our unit here. And the first one of this is volume. We know volume is represented by a capital letter V. What we need to understand with gases is that the volume of the particles themselves, unlike in solids and liquids, the volume of solids and liquids are made up of the volume of the particles. But with gases, the volume of the particles themselves are much less than the volume of the space that they occupy. The particles, again, unlike solids and liquids, are not touching. So these particles actually represent just point masses. So we basically have just a point in space that has mass is the idea. Gases also can be compressed, for instance, like with a scuba tank or car tires. With a scuba tank, if we had just regular air, unpressurized air, and uncompressed air, you wouldn't be able to breathe underwater for half an hour, with that volume. It would not work. You'd have probably 3 or 4 breaths and then you would be done. The second consideration, or the second property of gases that we want to kind of take a closer look at, is temperature, represented by the capital letter T. And what we have to understand with that is that the particle motion increases with increasing temperature. And this because as they move faster, they get more kinetic energy. So you can see there with the kinetic energy equation, we have V, which is our speed. So as the temperature increases, the speed is going to increase because what we're doing is increasing the kinetic energy. We can't change the mass of the particles, but we can change their speed. Now, those two are actually, common with, volume we have with liquids and solids, we have temperature with liquids and solids, but pressure is very unique to gases. And this is a force over a given area. There are many different ways to express pressure, and so this is going to mean that sometimes we are going to have to convert. So what I have here are not only our units of pressure, but also how they are related to each other, so we can actually use these to convert them. And you actually have some practice here with some pressure conversions. All right, so 1 atmosphere is 101.3 kilopascals. Kilopascal is actually not the kilopascal, but the pascal is actually the SI unit of pressure. But that is also equal to 760 millimeters of mercury. We tend to use that for things like blood pressure. That's what we measure it in, which is also the same as torr. Those units are the same, just different names. 1.013 bars, or barometric pressures. We have 14.7 psi's, like what you use in your tires, or 29.92 inches of mercury. So that's often given with barometric pressure. They actually measure how much the mercury actually rises or falls in a special type of tube called a barometer. All right, so let's get started here with some of the simple gas laws. And the first one we want to look at is Dalton's law of partial pressure. And yes, this is the same Dalton that we dealt with our atomic theory. So he stated that gases in a mixture behave independently of each other. So what he stated in his law was that the total pressure in a mix of gases is the sum of the partial pressure of the individual gases. So each gas exerts its own partial pressure, so that's that pressure of that individual gas. So the mathematical statement of this is that the total pressure, PT, is the pressure of the first gas plus the pressure of the second plus the pressure of the third, and so on. Now, in the laboratory, we typically, when we are collecting gases, let's say, for instance, like we're collecting hydrogen gas, all right, like here, we're decomposing something and we're giving off a gas. What we do is we use water displacement. So this beaker was actually initially filled with water. And what happens is the gas gets forced out and it bubbles up through and it actually pushes down the level of that water. That actually lets us measure that volume, but because it's collected over water, remember we also have water vapor mixed in here because there's always a little thin layer of vapor of whatever liquid we're using over the top. So in this case, the water vapor is actually going to contribute to the total pressure of the gas. So for example here, my total pressure is my dry gas plus my water vapor. So in order to figure out the pressure of just the dry gas, you have to take the total pressure and subtract the pressure of the water vapor, which you can do using a vapor pressure chart, which you guys have. What you will find on there is you need to find the corresponding temperature, and then that will give you the water vapor pressure that you would subtract. And we'll see that on one of our practice problems. So let's take a look at our first one here. So atmospheric pressure is 101.3 kilopascals, and this air is a mixture of nitrogen, oxygen, and argon as 78, 21, and 1% respectively. Calculate the partial pressure of oxygen. So we know the total pressure here is 101.3 kilopascals, but we don't have nitrogen's partial pressure and we don't have argon's. So we have to kind of think of this in a little bit of a different way. This 101.3 kilopascals represents the total pressure. Okay, so we know that we would add those together. But in this case, the total pressure is 100% of the pressure. So that means that of that 101.3 kilopascals, 78% of that pressure is coming from nitrogen, 21% of it is coming from oxygen, and 1% of it is coming from argon. So if we're trying to calculate the partial pressure of the oxygen, what we need to do is we need to take that 21%, change it to a decimal, multiply it by our total pressure, and you'll see right here we get the partial pressure of the oxygen is 21.3 kilopascals. Okay. All right, so the second problem here. Hydrogen gas is collected by water displacement at 18 degrees Celsius. The air pressure on that day is 744 millimeters of mercury. Calculate the pressure due to the dry hydrogen gas. Now, we know, because we've talked about it, that the total pressure of that gas that's in there is the pressure of the hydrogen and the pressure of the water vapor. Now remember, the water vapor pressure we will actually get from a table that I'll show you here in a second. Now, but what is the total pressure of these two? Well, if the atmospheric pressure that day is 744 millimeters of mercury, the pressure on the inside of the container is also going to be the same. Right? So what we would do is we would take 744 millimeters of mercury, and that is equal to the partial pressure of hydrogen, which we are looking for. And when we look it up on the table, we would find that the partial pressure of water vapor at 18 degrees Celsius is 15.5 millimeters of mercury. So all I have to do is algebraically rearrange that, and I get the partial pressure of hydrogen is at 728.5 millimeters of mercury. Now let me show you this vapor table that I was talking about. So here we have our temperature. Okay, so we go down to 18 degrees, and you'll see right here the partial pressure of water vapor at that temperature is 15.5. And that's all you need to do. It really is that simple. All right. Problem number 3. Below are diagrams of two apparatus. So this is a container here that is sealed, and this is a container here that is sealed. Basically, here is there's this gate that's between them, the stopcock, but it's closed off. So all of the helium is in here, and all of the neon is in here. So we need to determine the total pressure of each gas when this is opened. We have to assume no chemical reaction takes place between the mixing gases. Now, this sounds like it's a partial pressure problem, and it kind of is, but the problem is because I have all of the helium trapped in here and all of the neon trapped in here, notice that the volumes are different. So if you think about it, if I release this, the helium is going to move and fill both sides, and so will the neon. And now we've not only going to change the pressure, okay, because we're going to change the number of particles that are colliding into the sides of each of these tanks, but we're also going to be changing the volume. And Dalton's law did not actually cover that. So we know that there's other things that are going on here. So in order to solve a problem like this, we need some better gas laws. And that's what we're going to look at here, is some of the other gas laws. All right. And with the gas laws, what we are doing is we're actually changing one or more of the conditions of the gas. So these are mathematical statements relating to the variables of the gas. All right, the first one we're going to look at is Boyle's law. And the mathematical, Boyle's law was he was actually the first to find that gases are compressible. So if you look at that year, 1662, that was pretty early. He found the relationship between pressure and volume. And basically what he says is that volume increases, pressure decreases. This is why, and that's why I have marshmallows in a vacuum jar. If you take a peep and you put it in like a bell jar and you pump out the air, which we can do, the peep actually magically grows. And that's because what you're doing is you're actually lowering the pressure of the gas because you're taking away gas particles, and that means that the volume is going to increase on the inside. Those holes get bigger and it looks like the peep gets gigantic. So this is an inverse relationship. So the law basically states that at a constant temperature, the volume is occupied by a gas sample varies inversely with the pressure. It assumes that the number of moles, that's what N represents, is constant. So we don't change the actual, we don't add more gas or anything. We keep that the same. All right. So the mathematical statement is that P1V1 equals P2V2. Okay. So let me draw that here on our what the axes would look like, or what the graph would look like. So basically, as I'm increasing one, I am decreasing the other. Okay, so it could look something like this, or it could even look something like that. That's what an inverse relationship actually looks like. Okay. All right, so our first problem here. A sample of oxygen occupies 10.0 liters under a pressure of 790 torr. At what pressure would it occupy 13.4 liters if the temperature did not change? So let's take a look here. So we're using the equation here, P1V1 equals P2V2. Now, it doesn't matter which one you substitute in. I usually use the convention that 1 is what I'm starting with and 2 is what I'm ending with. And that way then I always keep my things grouped together. So in this case, my starting my starting pressure is 790. That's actually a typo there. It's supposed to be 790, and the answer is based on 790 torr. And the volume is 10 liters. And then I'm solving for the second pressure when it is under 13.4 liters. So I take 790 times 10 divided by 13.4, and I get this on my calculator. So I need 3 sig figs for this. So the 5 is going to change that 9 to a 0. So I need 590, and that decimal point is needed for sig figs. If I don't have it, and I can't put a 0 after it, but if I don't have it, I don't have 3 sig figs. Okay. All right, so that is Boyle's law. The second law we're going to look at here is Charles' law. And Charles' law shows the relationship between temperature and volume. He actually came up with this relationship, but it didn't really become a law until about 1800 because we didn't have accurate thermometers until about that time. So he actually came up with the idea a lot sooner than that, but we didn't actually officially adopt it until then. So basically what it says is the temperature increases, the volume decreases. So this is a direct relationship. And so what happens, and this would be like an imploding 55-gallon can of whatever. So you can actually do this, and I think Mr. Phillips, I think, has done this for you, where you take boiling water from a soda can and you flip it upside down in cold water, and it causes the temperature to decrease, which means the volume is going to decrease, and the can just magically crunches in on itself. You can also do that with a 55-gallon can, which is pretty impressive. But anyway, you can do it on a much smaller scale with just a soda can. So the statement of the law says that at a constant pressure, the volume occupied by a gas varies directly with the absolute temperature. And this is key. We have to be in Kelvin with temperatures for all of our gas laws. If we are not in Kelvin, the mathematical equations actually won't work. So you have to, that is one thing that you have to be really cognizant of and not forget that we have to do that. Again, just like Boyle's law, this assumes the number of moles of the gas is constant. So here's the mathematical statement of the law. V1 over T1 equals V2 over T2. A lot of times we're solving for temperature, so you can actually rearrange it to say T2 equals V2, T1 over V1. I kind of just memorized this one here just because it makes it easier and I can solve for any variable without a problem. So again, with my relationship, if this is my temperature and this is my volume, okay, it's a direct relationship. Okay, so which would be like this, or even something like that. Okay. All right. So let's move on to an example problem here. A gas sample at 83 degrees Celsius occupied a volume of 1,470 cubic meters. At what temperature in Celsius will it occupy a volume of 1,250 cubic meters? So our first step that we need to do is to change that temperature, any temperature, to Kelvin. And always do that first because you will forget otherwise. So we just take 83 degrees Celsius and add 273, and I get 356 Kelvin. Now I can set up my mathematical arrangement. Remember, we're using V1 over T1 equals V2 over T2. So I set it up this way. Okay, so this is my starting volume and my starting temperature, my ending volume, and we're solving for my ending temperature. That gives me this. Okay, I need 3 sig figs, okay, which means 303 Kelvin, and then all I have to do is subtract that 273 to get my final temperature, which is 30 degrees Celsius. Now, really what I need is a dot there, okay, a decimal there, so that I have 2 sig figs. Okay. Now, the next law is called Gay-Lussac's law, and so now we've related pressure and volume, and then temperature and volume. So that leaves that we need to, of the 3 big ones, we need to relate pressure and temperature. And it states that as temperature increases, pressure increases. So again, this is a direct relationship, just like Charles's law. As one goes up, the other goes up. So the statement of the law states that at a constant volume, the pressure of the pressure exerted, I shouldn't say occupied, this should say here, because pressure doesn't occupy, it should say exerted. Sorry, typing with or writing with this is not as easy as it sounds. So you want to change that. My lovely handwriting. Okay, you try writing with a mouse and see how it goes. So the pressure exerted by a gas varies directly with the absolute temperature. And again, the law still assumes that our number of moles is constant, so that hasn't changed. All right, so if we take a look at the mathematical statement, it looks a lot like Charles's law because, again, it's another direct relationship. So if I have pressure here and my temperature here, the graph would look the same too. It's going to be direct like that or direct like that. Okay. All right, so problem here. Before a trip, the pressure in a car tire was 1.80 atmospheres at 21 degrees Celsius. At the end of the trip, the pressure gauge reads 1.90 atmospheres. Calculate the temperature in Celsius of the air inside the tire at the end of the trip. and we have to assume the volume of the tire does not change. So again, the first thing that we need to do is change that temperature to Kelvin. It's just like with Charles's law. Any temperatures we have to have in Kelvin. Part of it is because we can't deal with negatives, because the negatives actually throw things off. We can't have a negative volume, so we can't really have negative temperatures or negative pressures. Well, we can have negative pressures, but that's beyond the scope of this course. So anyway, so we changed our temperature to Kelvin, and then we can go ahead and set up our mathematical proportion, essentially. Okay, so I've got my first pressure over my first temperature, and my second pressure over my second temperature. When I rearrange that and solve it algebraically, I get my second temperature is at 310.33. I need 3 sig figs, so that becomes 310 with the decimal there, okay, Kelvin, and I subtract 273, so then I get 37 Celsius as my final answer. All right, so up to this point, our gas laws have dealt with only 2 variables, all right, and but sometimes we can change more than one, and so let's look at when we involve all 3 variables. Okay, so then that leads us to what we call the combined gas law. And the combined gas law shows the relationship between all 3. So you've got the relationship between the pressure, volume, and temperature. And the reason it's called combined is if you think about it, it's really taking Boyle's law, Charles's law, and Gay-Lussac's law and putting it all together. So it takes into account the last laws that you have learned. It allows you to vary more than one thing to determine the outcome. So if you look at the mathematical statement here, let me just do a little playing around with it. If I cross off my pressure here, okay, you can see I have V1 T1 equals V2 T2. Okay, that is Charles's law. All right. If I cross off my temperatures, P1 V1 equals P2 V2, I have Boyle's law. And if I take off my volume and I look at my pressures, P1 T1 over P2 T2, that is Gay-Lussac's law. So like I said, this is accounting for all of the previous ones that we have had. Okay. Now, especially with this law, we sometimes use something called STP. And no, that does not stand for Stone Temple Pilots for my rock fans out there. So it stands for standard temperature and pressure. And so you have to understand what standard temperature and pressure is. And yes, we have seen this before, and I told you guys just to ignore it, but now we're actually going to have to look at what it is. So at standard temperature and pressure, what that means is my pressure is 1 atmosphere, and my temperature is 0 degrees Celsius, which remember is 273 K. That is something that you're probably going to want to jot down and use on your note card, all right, because it's not something that is automatically included for you it actually is, but it's kind of buried, so I would think that having it more accessible on your note card for the final would be actually very helpful. All right, so let's take a look at a practice problem here. So a sample of gas occupies 12 liters at 240 degrees Celsius and a pressure of 80 kilopascals. All right, at what temperature in degrees Celsius would this gas occupy if 15 liters at what temperature in degrees Celsius would the gas occupy 15 liters if the pressure was increased to 107 kilopascals? All right, so again, just like before, the first thing we need to do, well, we're going to use the combined gas law, and we need to convert our temperature to Kelvin. That's got to be our first thing. Then what we do, we are trying to find the second temperature here, so we can plug in everything else. So 80 times 12, okay, divided by 513 equals 107 times 15 divided by T2. And I end up with my T2 on my calculator as such. I need 3 sig figs, okay, so that rounds to 858 K. Sorry, I typoed that one. And when I subtract 273, I end up at 585 degrees Celsius. Okay, So those are the simple gas laws, and with those you should be able to complete the gas laws worksheet problems A. And then for your next video, what we will be doing is we'll be going into the Avogadro's law as well as the ideal gas law, which are a little bit more complicated of gas laws, just because it also takes into account the number of moles.